In this lesson, we're going to learn about binary numbers. C++ doesn't natively support binary literals, so we'll need to create a couple of functions to help us visualize this. Fortunately, creating those will help us learn how binary numbers work. So let's go ahead and create a project. Console application, as always. We will just call it binary. There we have our default empty program. In decimal numbers, place value is kind of obvious. For example, the number 234. In decimal or base 10, the 2 is worth 200, the 3 is worth 30, and the 4 is worth 4. And that's because each decimal place has a certain value. This is the number of ones, this is the number of tens, and this is a number of 100s, and so on. Now in binary we have a similar situation, but we only have the values 0 and 1 instead of 0 to 9. So the number 111, we can see that is the ones. Now that isn't the tens, it is in fact the twos, because we only have 1 and 0. So that's 1, 1, 1, 2, and the next column is the 4s. So that number would be 1 plus 2 plus 4, which is 7. And we can go on, we could add another 1 in the 8s column, and we would have 15, 16s, and so on and so forth. So let's see what that means in practical terms. And we'll explore that by creating a function that takes a list of binary digits or bits in the form of a char array and converts them into an actual number. So we'll return an int. Bits to int is the name of our function, and it will take the bit list. And we also have to pass in the number of bits so that it can do the calculations accurately. And our main function will simply have a chr array, my bit list equals, and we'll just do a byte or 8 bits of information, all ones. Let's call it result equals bits to int, and we will pass in our bit list. And the number of bits is 8. And we will output that to the screen. So I'm not going to say byte value, I'm going to say result is result. Keep it simple. So we now have to fill this in, but let me just build, make sure we have no errors. We have a warning of no return, but we'll get to that in just a moment. And we have something else there too. Go. My bit list was not declared in this scope, and that's because I put those square braces indicating the array in the wrong place. We have them after the identifier, not after the variable type. So let's build that. We're good to go. And let's fill out this function. First thing we need in this function is a return value. I'll put int result, and I will initialize that to 0. And at the end of the function, we just return result. And all our logic goes between the two. Now, what we have to do is work our way through this list of bits and assign a value based on the place. Now, let's figure out how we can determine what that value should be. Now, we know that the rightmost bit has a value of 1, and each bit to the left of it has a value twice as much because it's powers of 2. So that is in fact 2 to the power of 0, 1, 2 to the power of 1 is 2, 2 to the power of 2, and so on, up to 2 to the power of 7, which is 128. So this bit is worth 128. But we need to calculate that just so that we can make this function more flexible. And to do that, we need to include our math library. Include math h, that's how you include that library. And we will say our maximum bit value, I'm just going to call it bit value. I'm actually going to call it place value, that's a little more accurate. Place value pow, which is the power function, 2 to the power of bit count. In fact, that's going to give us 1 too many because it's a 0-based array. Remember, there are 8 bits and we want 2 to the power of 7. So it's actually going to be bit count minus 1. And I'm also going to need a character that will hold a single value from our array bit list. And we're going to go through those using a for loop. Starting at 0, going all the way to bit count minus 1. Remember, we have 8 bits, and that's 0 through 7, so we want bit num to finish before it gets to bit count. And of course, we're going to increment, bit num. Can't type today. I have an error there somewhere because it wasn't auto-completing, so let's build and see. No, I only see unused variable warnings, that's fine. So let's continue. I'm going to say that bit is bit list subscript bit num, bit number. So the first time around the loop, we're going to take the first item out of bit list, i.e. subscript 0, which of course will be that one, and work our way down. And our place value will start at 128, and it will effectively half for each place we move to the right. So 128, 64, 32, 16, 8, 4, 2, 1. So we're going to say result is incremented by, plus equals is the shortcut. That means add the right hand side to result and store the result in result. Bit is equal to 1. Then we want to add place value. Otherwise we want to add 0. We're effectively assuming that we're going to have a 1 or a 0. Now, in fact, we could have a 1 or any other symbol based on my logic here, and any other symbol, any symbol that isn't a 1 will be treated as a 0. But that's fine. We don't want to add a lot of error handling at this point. That would just obscure the code. And of course, we want to halve the value divided by equals bit value. 2. Now, in fact, if you ever code for performance, division is slightly slower than multiplication in most processors. So what I'm going to do, instead of dividing by 2, I'm going to multiply by 0.5. It's just slightly quicker. We don't really need the performance in a program this simple, but you know, if you're coding for performance, that gives you a quick win right there. So let's go ahead and build this. We have one error, and that is because I misnamed my variable. It's not bit value, it's place value, of course. So let's replace that. Let's rebuild. We have no errors, no warnings. Let's go ahead and run it out, see what we get. build and run. Okay, the result is 255. Now, if you're familiar with binary, you'll know that 8 ones works out as 255, but we could do 7 zeros and a 1. Just count 1, 2, 3, 4, 5, 6, 7, 8. And if we build and run that, we will of course get 1. 1 is the same in any base. Space there, I don't want. Do 1, 1 should be 3. 1 plus 2 is 3. And it is indeed. And so we did 4 ones. Have to know that's 15. 8 plus 4 plus 2 plus 1 is 15. Run that out, we get 15. Now this is fine for positive integers, but what about representing negative integers? Well, we need to do that too. And the technique used in computing to represent negative integers in binary is called 2's complement. So we're going to modify our program that lets us do that. But first of all, the way 2's complement works is we look at the most significant bit in our list of bits and we make that a negative value. So in this case, if we had a 1 there, it would become negative 128. All the other bits retain their positive place value. So in effect, you have a positive value that can't be quite as high as this negative value. And you'll see what that means in practical terms as we modify our function. So let's scroll up to modify our function. So we'll modify our function to take a flag called 2's complement. It will be either true or false. Now at the end of our statement, we're going to create an if clause. If 2's complement is true and bit list position 0 has a value of 1. Remember, if it's a 0, we're saying it's a positive number. If it's a 1, we're saying it's a negative number. Then we've already added this in our loop as its positive place value. So we need to subtract it twice. And the easy way to do that is simply to take the place value of the next figure and subtract it. Now that's a bit of a programming trick. It's not 2's complement, but it does give us a convenient way to do that. So our place value 2 to the power of, or the next position over would be 2 to the power of 1 more than this, so it's actually 2 to the power of bit count. We subtract that from the result. And even though we've done the work twice, we added in that last place, but we subtracted twice the amount to give us our 2's complement value. So let's run that and see what we get. I'm going to put in another number. I'm going to put all 1s in again. Now we do need to pass that flag in here. Initially I'm going to pass it in as false so that we have a comparison. Let's see that we can build. We can build okay. Let's run it and we get 255, which is what we had before. But now if I pass in a value true, which turns this into 2's complement, telling our function to treat this negatively. We run it again and we get -1. So all the 1s is basically -1. We have positive 127 here if you add up all those place values, and negative 128 here. So that gives us an overall total of -1. And if we decrease this by 1, rebuild, rerun. You can see we get -2 for the same reason. Now if we set everything to 0, we will of course get 0. But the most we can have in positive numbers is this. 7 ones and a 0. You know, if we flip that bit and reset all these to zeros, which would be the next number in line, we would have gone to a negative number. So from here we have 127, which is our highest positive number, and if we increment this by 1, which is effectively that, you can see the next number we get is -128. So that's our range of numbers. We've gained a sign, but we've sacrificed half our range. You know, we don't go from 0 to 255 anymore. We go from 127 to -128. But that is in effect 2's complement. Now we can convert from our string representation of a binary number to an integer. We need to be able to visualize the conversion in the other direction. So let's go ahead and create the reciprocal function, which we will call show bits. Value, and we also need the bit count. And again, we need our most significant value. Now for brevity, I'm going to skip 2's complement and just focus on positive conversion. You can see it's essentially the same loop as before, the same place value. Again, I called it bit value, seem to have a mental block on that. Call it place value. We'll say the bit is 0 unless otherwise. What I'm going to do is say if value, and value is what we passed in, is greater or equal to bit value, place value, then we're going to change our bit for 1. And we're going to decrement the place value. We're going to decrement the value by the place value. We will display a bit, and we will halve our place value. And my value equals 15. Out 15 in binary is show bits 15 8 places, 8 bits rather, and out and line. Let's build that. Let's run it, see what we get. Just before I do, I can see that I've declared the value there and I've neglected to use it everywhere, so let's go ahead and fix that. My value, there we go. That way we haven't repeated this number 15 everywhere. So rebuild, rerun. You see 15 in binary is 0000 1111. That's 1 plus 2 plus 4 plus 8 is 15. So now we have a way to declare binary digits and convert that to a real world variable, and we have a way of displaying our binary digits from a real world variable. Now I highly recommend setting a breakpoint in both of these functions and stepping through them, watching each of these values, and by the end of it you'll have a very good idea of how binary numbers work, certainly in relation to conversion between decimal and vice versa. Now, as you might have guessed by now, in C++ there's an easier way to do what we've just done, and let's quickly demonstrate that. I'm going to add a couple of libraries, one called bitset and another one that will help us called string. And the way we use the bitset library is like this. The bitset type with a type specifier with the number of bits in it, 8. Our identifier, I'm just going to call it my bitset. And we can initialize it. Notice there's no equal sign in the initializer. We have parentheses instead. And we need to specify that it's a standard library string. And I'll do 0, 1, 1, 1, 1, 1, 1, 1, which should be 127. And let's display that. A binary number. My bitset. And we have a method on that object called toString. It's a decimal value of. And we also have a to unsigned long. So let's build that. We have an error here somewhere. There we go. I missed out one of my stream signs. Let's rebuild. And fix that too. Third time's a charm. Let's run it, see what we get. We go, the binary number 00111 has a decimal value of 127, just what we would expect. And we can use a bit set in the other direction too. We can initialize it with a numeric literal. My other bit set. We can simply initialize it with, let's say, 15. Which should give us 4 ones. C out. Number. Other bit set to new long as a binary representation of set to string, and it's just the reverse of the previous line. We're going to show the long value first, and then we're going to show the binary representation. So let's build that. We have another error. Oops. Fix our error, rebuild, and let's run that out. And there we are. The number 15 has a binary representation of 4 zeros and 4 ones. Now, of course, if we'd specified a larger number of bits in here, say 16 bits, we would have 8 more zeros before these, 12 zeros and 4 ones. But that in a nutshell is how you can shortcut all of this conversion using the bit set library.